conditional probability. The probability of an event under the condition that some preceding event has occurred is called conditional probability. The conditional probability that event A occurs given that event B occurs can be written this way. And so we get this formula. The conditional probability of event A given event B is defined as the probability of A and B over the probability of B, where the probability of B does not equal 0, because then you'd get a divide by 0 error. So the second part is always your given, right? So it's the probability of some event given the given. And by the way, that symbol on your keyboard, it's right under the delete key on the right-hand side. It's just a straight line, but it's a fancy symbol straight line. It's not a letter or anything like that. It's definitely not a slash. Do not use a slash for that. So the probability of some event given the given is the probability of the two events occurring divided by the probability of the given. So I'm going to keep saying this because it's important that you know that the second thing is the given. That's the thing that we know. It's if this is true, what's the probability that this is also true? If B is true, what is the probability that A is also true? Danielle Jones works in a medical research laboratory where a drug that promotes hair growth in balding men is being tested. The results of the preliminary tests are shown in the table. What is the probability that the test subject's hair grew given that he used the experimental drug? So we're looking for the probability that the subject's hair grew given that he used the experimental drug. So since this is the given, this is the thing that we know. So we're only going to be looking at the people who use the drug. So our formula from the previous page says that we're going to do the probability that the hair grew and used the drug over just over the probability of using the drug. So when we have a table like this, this is called a contingency table or a two-way table. And so we use this a lot for conditional probability, but what we're going to want to do is to tally up the row and the column totals. So there are 2,800 people with hair growth and 1,200 without, which is going to give us a total of 4,000. And of the ones using the drug, there were 2,400 using the drug and 1,600 using the placebo, which also gives us 4,000. So what we need here, we need the people whose hair grew and used the drug. So the people who had hair growth and used the drug are going to be, the probability of being in that group is 16,000 out of, or 1,600 out of 4,000. And we want to divide that just by the probability of using the drug. So how many people use the drug? That's 2,400 over 4,000. Right? If we're randomly picking one person, the probability that they used the drug and had hair growth, 1,600 out of 4,000. If we're randomly picking a person, the probability that they used the drug, regardless of whether or not they had hair growth, is 2,400 out of 4,000. And so we can keep, change, flip these fractions. Make that 4,000 out of 2,400. 4,000s cancel. This is 16 out of 24, which is 2/3. right? So, given that they used the drug, the probability that they had hair growth is 2/3, right? Out of all the people who used the drug, 2/3 of them had hair growth. Danette tosses 2 coins. What's the probability that she has tossed 2 heads, given that she has tossed at least 1 head? So if you're tossing 2 coins, you have 4 possibilities, right? You have 2 heads, you can have a heads and then a tails, you can have a tails and then a heads, or you can have a tails and then a tails. Given that she has tossed at least 1 head, means we're not looking at the scenario where there are 2 tails. So the probability that she's tossed 2 heads ends up being 1 out of 3. Another way that we can do it is, again, using that formula. Probability of 2 heads given at least 1 head is the probability of 2 heads and at least 1 head over the probability of at least 1 head. Now, 2 heads and at least 1 head is just the probability of 2 heads, right? Because in order to have 2 heads, you have to have at least 1 head. So, at least 1 head, having 2 heads is 1/4. The probability of having at least 1 head, you've got 3 options with at least 1 head. So 1/4 over 3/4 is 1/4 times 4/3 if we keep change flip, and that also gives us 1/3. So we can do it using the formula, or we can just say, okay, out of all of the scenarios where there's at least 1 head, of which there are 3, how many have 2 heads? And the answer is 1. Alfonso is conducting a survey of families with 3 children. If a family is selected at random, what is the probability the family will have exactly 2 boys if the second child is a boy? Probability of 2 boys given that the second child is a boy. Right? So that's going to be the probability of having 2 boys and the second child is a boy, divided by the probability of the second child being a boy. So the probability that the second child is a boy is 1/2, right? 1/2 probability the second child's a boy, 1/2 probability the second child's a girl. Given that, so the probability of the second child being a boy and having 2 boys, if there are 3 children, you have 8 different scenarios, right? Like, the probability of 3 boys is going to be 1/2 times 1/2 times 1/2, which is going to be 1/8. So there are 8 different ordered arrangements of 3 children by gender. And so how many of those scenarios have exactly 2 children and the second child is a boy, right? Exactly 2 boys and the second is a boy, right? Ones with exactly 2 boys, you can have boy, boy, girl, or boy, girl, boy, or girl, boy, boy. We're not counting the one where the second child is a girl, so that gives us 2 out of 8 scenarios where the second child is a boy and there are exactly 2 boys. So 1/4 is the probability that there will be 2 boys and the second child is a boy. 1/2 is just the overall probability that the second child is a boy. And so we can 1/4 times 2/1 is 2/4 is 1/2 is our probability. Again, we could also write out the arrangements, right? You can have 3 girls. You can have girl, girl, boy, girl, boy, girl, boy, girl, girl. And then you can have boy, boy, girl, boy, girl, boy, girl, boy, boy, and then you can have 3 boys. So these are 8 different ways that you can have 3 children. And so given the second child is a boy means we're eliminating all of the cases where the second child is a girl. So that gives us 4 cases where the second child is a boy. And then we want the number of arrangements with exactly 2 boys, and that's going to be this and this. So 2 out of 4, or 1/2, is the probability that the second child will be a boy, or that you have exactly 2 boys given that the second child is a boy. A 12-sided dodecahedron has the numbers 1 through 12 on its faces. The die is rolled once, and the number on the top of the face is recorded. What's the probability that the number is a multiple of 4 if it is known that it is even? So all multiples of 4 are even. That helps a little bit. So the probability that it's a multiple of 4 given that it is even is the probability that it's a multiple of 4 and even over the probability that it's even. And again, we know the probability that it's even is 1/2, right? Numbers 1 through 12, half of those are going to be even. The probability that it's a multiple of 4, the multiples of 4 between 1 and 12 are 4, 8, and 12. So that's 3 out of 12, or 1/4. 1/4 divided by 1/2 is going to be 1/4 times 2/1, which is, again, 1/2. And again, if we look at the numbers, right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, it is known that it's even, so we go through and we delete all of the odd numbers. We're only looking at the even numbers. And we want to know there's 6 even numbers here, and then we want to know what's the probability that it's a multiple of 4, 4, an 8, or a 12. 3 out of 6 equals 1/2. The formula tends to be the easiest way, though, when you're working with bigger numbers or scenarios where you can't write out all of the whole sample space like this. And that's it for 13.5. Tune in next time for our last video, 13.6.